Our next speaker will be Carl Scheffler, speaking about distributed pub/sub with Apache Kafka. Carl, take it away.
Great, thanks. It's too soon for that, you don't know what I'm going to say yet. So yeah, my name is Carl. Just a little bit about myself. So I trained as sort of a mix between a computer scientist and an applied mathematician. So I code as, I'm a software developer, take a lot, as you can probably tell from the shirt. But I do this for the sake of doing sort of interesting data analysis and machine learning sort of stuff. So my interest here and the sort of the point of the talk is to talk about infrastructure. How do you get information data from one point to another so that you can do sort of the interesting things that I like doing with it? So I did my PhD in machine learning, and then after that, that was overseas, came back, did a bit of work in an education startup for a couple of years, and then moved on to Takealot, where I am now. But okay, enough about me. So who's Kafka? So apart from being a literary figure, actually I don't know why the project was named Kafka in the first place, but it's basically a system for handling very high throughput events, messages, generated in a distributed way, so in various components of whatever your software stack is. And that has all of the sort of the good stuff that you want. So it's resilient. So if a node, it uses consumer grade hardware, you can have lots of nodes in a cluster. If a node falls over, hopefully you replicated your data. That's a configuration parameter which you are allowed to set to 1. But that's a bad idea. Then so it can recover from failure and all that sort of good stuff. It was originally developed by LinkedIn. They handle lots and lots of traffic. So the most recent article where they have a number in terms of the number of messages they generate per day was written in March of this year, and then they claimed they generate about 800 billion messages a day. So that's pretty intense. I think peak usage is something like 11 million a second or something like that. They open sourced the project in 2011. It became a first-class Apache project in 2012, which is amazing for the rest of us. So it's actually really, really cool software, really cool infrastructure. And I'll tell you a little bit more about how it works. The basic idea, sorry, this is a bit small, but I'll talk about it anyway. And I realized I was sitting over there earlier and people at the back can maybe not see the bottom, so I'll sort of try and say what's on the slide as well. So the whole idea, so when you think about messaging and distributed messaging and all of this sort of stuff, you might think of other things like maybe RabbitMQ or other queuing systems. So why am I talking about a log? Well, so first off, this is in the middle of the slide, a queue is a bit like a log that hasn't happened yet. So a log tells you what happened and when, and a queue tells you things that you would like to happen, typically. I mean, there are other use cases, but it's sort of the rough idea. But basically, they're the same thing. It's an append-only data structure. It's strictly ordered. It's sequential, because it's append-only. And it records what happened or will happen, and when. Where when is not actually the timestamp. When is the index in the queue or in the log. You can have a timestamp as well. That's optional, but your timestamps may or may not be strictly ordered. If your servers are if the clocks on your servers are slightly out of sync, you can see sort of inverted timestamps and things like that. But the index of an entry in a log is completely deterministic. So why is this important? It seems like a very sort of specific, trivial thing. The reason why it's really important is that it gives you something that's very deterministic. You know exactly what happened and when in the sort of index sense, which means you can replay anything. So if you have some sort of log, that log state changes maybe in a database, you can recover the state of your database by replaying through the history in the log. And so because the log is deterministic, and assuming that your software is deterministic, which it hopefully is, you'll get back exactly where you were before, if you're actually replaying some sort of state. So this sort of fairly simple idea allows you to do things at huge scale, because you can do that very simple thing, appending stuff to a log, or reading from something that is completely linear, really, really fast. Operating systems, file systems, all of these things are optimized for exactly that. Write things really quickly as long as you're writing sequentially. These days it's changing a bit with solid state drives and so on. Or if you're reading things sequentially from a file, that's really quick, and the operating system does cool things like reading ahead and caching stuff and so on. So what the log gives you is, so firstly, an audit trail of what happened, replication, reproducing state, as I said. So I'm just reading through for the sake of the people who can't see. Notification, so if you're interested in a particular entry or type of entry in a log, whether it's part of your monitoring system for your servers, or whether it's maybe some state transition on some sort of object in your system. You can look out for those and then send off some other event, which also goes to the log, as it turns out, to notify somebody of something. And then aggregation. You can take these log files, go through them, and generate interesting reports or new data streams by aggregating simpler data streams. So that's basically, there are some details, but essentially Apache Kafka is a log. The details make it work, and so I'll talk a bit about those. So it's a partitioned log, which means it's not just one log file, you have lots of them. So each of the logs, if you look at any one of the particular logs, they satisfy everything I had on the previous slide. Strictly ordered, append only, etc., etc. The purpose of partitioning is to give you horizontal scalability. So rather than having just one log file running on one machine somewhere, you have a number of machines with a number of log files, one per partition. And that allows you to do things like take an incoming stream of event, spread the load across your writers. So the things that I'm going to start using some of the jargon, the producers, the things that generate events, can then talk to any one of the Kafka brokers. The things that are consuming events can consume from a particular partition. There's a restriction in Kafka, which might sound a bit weird first, but gives you a lot of performance advantage, is that if you're a consumer, you can only one consumer within a group can read from a particular partition. So let's say your service is running and is consuming events off Kafka, and let's say you have 3 workers running in your service, or you have 4 running. Each one of those you can only have one worker reading a particular partition. So you have 20 partitions, then you have to split them up between your 4 workers, and that's a hard rule. That doesn't mean you can't fire up more workers and reshuffle partitions. I'll do a little demo later to show you just that. But it just means that the partition, your number of partitions defines how many workers you can have, basically. But what that gives you is that you can, Kafka is very efficient at keeping track of how far a worker is through a log. It stores offsets. If one of your workers falls over, other ones can pick up where it left off because Kafka stores offsets, and so on and so forth. So it gives you a lot of benefits, even though it's a bit of a strict restriction. And then the sort of middle point there on the slide, something else is important, is there's no guaranteed ordering of any kind between partitions. So if you have 2 partitions, it could happen that a producer writes to partition 1 or partition 0 for a long time before writing anything to partition 1. Typically it doesn't happen, but you have no guarantees whatsoever. There are some ways of working around that. For example, when you produce messages and put them on a partition, you can tell Kafka which partition should be on based on a key. So you give it some value. It's typically something like an ID of something, some object, so a product that you're selling. So you take the product ID, you hash it, modulo the number of partitions, and you store it on that partition. So that at least guarantees that every event relevant to a particular product, if you use the product ID as your key, will end up on the same partition, which means if one of your consumers is reading from that partition, it will see all of the events for that product. So it gives you a way of splitting up all of your data based on something important to you, and you can specify what that is. And that gives you very good horizontal scaling. I mentioned some of these things already. I'll just go through them again. So Kafka is really fast, 800 billion messages a day, 11 million a second on I think they said the cluster sort of 50 nodes in it or something like that. So it's a sizable cluster, but it's still a ton of traffic. It uses what the operating system and the file system provides a lot. So it doesn't try to reinvent things like, should I put events in memory first for a while in order to batch them and then write the entire batch to disk? Or when I read stuff, should I read ahead because I know a particular consumer is consuming events and I expect it'll consume some more in the near future? It just doesn't try and implement any of that. It leaves that up to the operating system, because that's what operating systems do and have been doing for a very long time. So don't try and reinvent that wheel. Persistence, again, you're writing stuff to a file, straight to a file. So Kafka doesn't store produced events in memory at all. I mean, it has to make its way through at some point because that's where software runs, but it goes straight to disk. So you get immediate persistence in a file. And you can, so quite a neat feature is you can configure how long things persist for. By default, it's 7 days. So actually, if you log events, so this is where it's a little bit different from just a straightforward messaging, publish-subscribe messaging system. There are some others out there that are completely ephemeral. So you fire and forget. subscribers receive them or they don't, but you don't care. In this case, you fire and it gets stored somewhere by default for 7 days. And I think the longest one we have is 28 days at the moment. That's completely fine. We've considered pushing some of our logs up to maybe a year, so for something to do with users actually relevant for a longer period of time. So you end up with big files, but so what? The space is cheap. And one of the amazing things that gets you is that you don't have to do everything in real time, but you can. So you can choose your time scale. So if you're working in sort of data analysis stuff like I am, then actually you care about different time scales depending on what you're doing. If you're building some sort of real-time dashboard, something that looks a bit like Google Analytics real-time, then you really want stuff now with as little latency as possible, and you can do that. Or if you want to run some sort of batch job using Spark or whatever your favorite big data tool, you can consume a whole log in one go later on. So maybe your batch job runs once a day for updating models for recommending things, for example, and you can do that using precisely the same infrastructure as your real-time jobs. There's literally no difference between the two. You just choose when to start and stop your consumers. That's all. So that's really neat functionality. Speed, okay, I mentioned that already. So OSs are well optimized for this sort of stuff, and replication is easy as well. It's just the same file, the log file, on a different machine. So instead of if you set the replication factor to 3. Instead of writing a new message to one file on one server, it'll write it to one file on 3 servers. And that's a configurable thing. And if you wanted to restore your data, you just copy a file. Okay, so at Takealot, we sort of started introducing this earlier this year. And a big part of the reason, I don't have a nice picture, unfortunately, of what our stack looks like, mostly because it's very messy, but also because pictures take more time than words. So I'll hand wave a bit. But there's a big legacy stack, and one of the things we're in the process of doing is slowly but surely breaking that apart while keeping the site up, hopefully, into smaller services that communicate with each other and do all sorts of useful things. And importantly, what we don't want, what we have and what we don't want, is a monolithic code base, a monolithic database, and then this website that does absolutely everything, including the front-end stuff and the back-end stuff. There's thankfully a separate API for apps, mobile, all that, but it's still a pretty massive stack. So the problem there is your database is essentially one massive global variable. Any part of the monolithic code base can access any part of the database. And so you get a huge mess of code touching data absolutely everywhere. If you split things up into services, services are responsible for local data, and you can't access another service's data directly, so it's basically encapsulation. So that's great, but one of the things you really want with that is this kind of data bus where services can notify other services of what they're doing. So you have point-to-point communication between services. That's important, and that's not what I'm talking about. But you also essentially have publish-subscribe communication between services. So if I'll just stick to products. If I'm the product service and somebody updated the description of the product or the stock level or whatever, there might be other services that care about that. I don't know who all of them are, and I shouldn't care. So I just want to fire off an event to say that this happened. And it might happen a lot. It turns out that stock updates happen like tens of thousands a day and that sort of thing. So there's a lot of this stuff going on, and that's not even the busiest part of the stack. So that's sort of why we started looking at Kafka in the first place, is this kind of data bus for communicating between different parts of the system. And these are, so I'll talk about each of them a little bit, but these are sort of the things we've been using it for so far. So user tracking, that's essentially Google Analytics, but doing it in-house rather than giving it to Google. Because we have better control over our own data. So to see what's happening in checkouts, our checkout process, I think I'm allowed to say this, is terrible. So you want to figure out how to fix it. So you want to figure out where people drop off, what's the worst bit, and then the UX people redesign based on that, and then you repeat. So you monitor the new process, see what's going on. Recommendations. So that's one of the first things we did, is just because there wasn't really a recommendation system running, is just to see what's happening on the site in terms of, the typical thing that you would see on other online retail companies, where they'd say people who looked at this eventually bought this, that sort of thing. Common search terms, what do people search for, what things should we care about? So all of that sort of user tracking, sort of classic use case for this. A/B testing, so once you have a publish-subscribe infrastructure set up, you build an A/B testing service, and it just sends messages to this thing. So you tell it, register a test, please. here's A and B. If it's A, call this endpoint. If it's B, call that endpoint, and just fire off a message to tell me which one you did. And then after the fact, you can run either a batch job or something in real time that gives you some idea of what's happening in your test, whatever it is. Real-time dashboards already mentioned. Audit trails. So when you write everything to a database, it turns out you know where you are, but you don't know how you got there. And that's still true for a lot of what, and it's in the process of changing, but it's been true for a lot of what we've been doing. So, and probably top of the list was orders. So a customer phones in, they say, my order never got shipped, or I got this thing whereas I should have gotten that thing. So you want to be helpful, but it's quite tricky to be super helpful if you have no idea how we got from A to B. So we know what B is, and we know A was somebody placed an order, but we don't know what happened in between. So again, a classic example for that. Just with every state transition in an order, fire off an event, forget about it, something else picks it up somewhere else and does something useful with it. And then SQL trace. I just want to spend a sort of a minute on this. This is actually quite a fun one. So I said we have this big database, we have the big code, big stack, monolithic code base, and the code base basically can touch any part of the database, which is terrible. So one of the problems with trying to split this up is you want to build your order service, right? So it's a separate piece, but an incredible number of places in the code actually affect order state, not just reads, writes. So how do you find them? So there's a SQL statement somewhere in our case, a Python or a PHP file. We have a legacy PHP stack we're trying to get rid of, and we build new stuff in Python. So how do you find them all? You can grep, you'll probably find most of them, but you'll miss some. So what this does is so we use MySQL Python, and so we actually replace the query call in MySQL Python. So just overload it. So that for 1 in every 1,000 queries, the reason why it's 1 in 1,000 is there are just too many queries, so you can't log them all. But for 1 in 1,000, we log the query, the stack trace, the timestamp, and how long the query took. So that tells you where your slow queries are. It tells you, the stack trace tells you which part of the code touched, and the SQL query tells you which part of the data. You just log all of that. So that generates quite a lot of traffic, but you can process it after the fact. And if somebody says, why on earth did this thing change from this to this? As long as it's a systemic thing, so as long as it's not a once-off thing where somebody ran a query that screwed something up, if it's something that happens a lot, it'll be in that log because it's sort of sampled in an unbiased way. So we've been using that to build up a map of what parts of the code affect what parts of the data, reads and writes. And then that allows you to basically try and draw a perimeter around some table or tables in your database, cordon them off, pull them out, and make that a new service. It's a slow and painful process, but it's at least possible. So for orders, for example, just to give you some idea, it turns out there were 100 lines, different lines of code in different parts of the code base that affected order state. And just over 100, and finding them all would have been a real pain otherwise. Okay, this is what we do, just to give you some idea. We have a 3-node Kafka cluster, 3-node Zookeeper. So if you haven't heard of Zookeeper before, it's just a way of sharing global state between different services. So here you have 3 Kafka brokers, they're called brokers for some reason, and they need to coordinate with each other. Zookeeper does the coordination for you. I'm not going to talk about Zookeeper much, but that's what it's for. And we have that running on a data center. It's replicated in EC2. We replicate some of the logs from the data center to EC2 for ingesting into Hadoop and things like that. So at peak, we do about 200 messages a second, and average is about a factor of 10 less. So that results is about 1.75 million a day. So that's a lot. It's nowhere near what LinkedIn does, but it's not bad for a fairly straightforward 3-node Kafka cluster. And that's not something that's hard to set up. The Kafka, Apache, I think, has made them produce quite a good documentation of that. When I talked about real-time dashboard earlier, again, so I gave you some, so this is to give you some idea of performance, right? So there's throughput, peak throughput, average throughput, lag. So this is something you care about a lot when you do real-time stuff, real-time dashboards. So the real-time dashboard we have that aggregates and summarizes a bunch of stuff happening on the site has a typical lag of about 250 milliseconds. So I've seen it as low as sort of 120 milliseconds or so, and it can go up to, I don't know, maybe double that or so, and it depends obviously on lots of things happening. Just how that's measured is there's somebody does something on the site. The event, the PHP or Python code runs. It records its timestamp along with the event. It sends that off. That goes to Kafka in the data center. That gets replicated to Kafka in EC2. Our EC2 nodes are in Europe, so you lose about 60 or 70 milliseconds just due to the speed of light. There it gets aggregated by a consumer, and then that's what you see. So all of that takes 250 milliseconds. So subtract 60 or 70 for the speed of light. So something more like 180, which is pretty decent. It probably wouldn't satisfy everybody's real-time constraints, but that's definitely good enough for us. We also do things like index from Kafka into Elasticsearch to do. You can search for stuff after the fact and do more dashboards and so on, which is very, very handy, and that's easy to do. Okay, demo. Right. I am going to attempt a real live demo. Yeah. All right. Let's see. Okay. So I have installed Kafka. This is just there's something simple you can do, which is to just run a standalone local copy of Kafka. So it's running on my laptop. This is not what you do if you install it for production use. So it looks like this. Not very interesting. Start up Zookeeper. So this is the thing that does coordination between different Kafka brokers. It's not really necessary because I have one Kafka broker on my one machine, but it's a required piece anyway. So Kafka will complain if it can't find Zookeeper. Then I'll start Kafka. This is out of the box, right? So default configuration settings, nothing funny. Good. So they're running. Just to show you, I'll just clear this so it goes to the top. This is what the Kafka logs directory looks like. So I have a topic. I haven't talked about topics. It's just logs are grouped by topics. So basically, it's a useful way of saying these events belong together. So you might have an order tracking topic and a user tracking topic and a MySQL trace topic and so on. Just a way of grouping things. Each topic has its own configuration settings. I made a topic called test. It has 6 partitions from 0 to 5. And you'll see there's some other files in there. So it turns out storing consumer offsets and things like that are also just topics in Kafka because it's an event log, it's a message log. So it just uses its own infrastructure to do all of that, to provide that functionality. Okay, so at the moment, this isn't very large. It reserved some initial space. That 10 megabytes for each of the partitions is just initial space it reserved for its index file. Okay, now I'm going to start up 1 producer and 3 consumers, just to give you some idea of what goes on. It'll be fairly simple output. I don't imagine this will blow your hair back, but actually, given that this is completely out of the box and just running on 1 machine, I think it's pretty cool. So I'm going to start up a producer. Oh, I should show you what that looks like, I suppose. There's the producer. So I'll talk about PyKafka soon. So I import a Kafka client. There you'll see I pick my topic. I create a producer, and most of this is just fluff to count what's happening, right? I'm counting the number of messages sent and how long it took, and you'll see that output. What actually happens in terms of producing a message is there. You construct a message, which in my case is just a UUID, right, just for lack of anything better, and I produce it, that's it. It's asynchronous, so you can produce quite a lot of these in one go, and you'll see that in a second. But that's all. Really, the stuff around it is just to show something interesting on the screen. The consumer is equally simple. I have something called, there's a simple consumer and a balanced consumer. The balanced consumer is the thing you want to use. It automatically figures out how many consumers are running within a group and splits up partitions between them. That's balanced, so it balances partitions between the consumers. You'll see that soon. So you have to give it an identifier. I enabled auto-commit. You can choose to commit manually if you like. Tell it where Zookeeper is, and then similarly, you have already picked there. So I picked my topic up there. I create my consumer over here. There's again just a lot of fluff around here to produce some interesting output, but basically that's the interesting line. Consumer.consume. Run it in a loop. It'll block if there's no message and wait for the next one. So typically, if you have a consumer, you just run it and you leave it, and as soon as something interesting arrives, it does something. Yeah, and that's about it. The message contains some metadata, like which partition it's from, and I'll show that on the screen, what the value is and all that sort of stuff. Okay. So, running my producer. it'll print something every 5 seconds. So I'm just going to give it 5 seconds. There we go. So that's the first line of output. So it produced 7,500 messages in those 5 seconds. Sorry, 75,000 messages. So it's doing about 15,000 a second. So these are simple, short messages. If your message is longer, it'll take a little bit longer because disk writes and stuff like that. But this is sort of roughly what you can expect on this kind of setup, which is fairly simple. Okay, that's running. Oops, now I'm going to run my first consumer. Same story, produces output every 5 seconds. It'll show two things. One is the number of messages consumed. Again, just to give you an idea of throughput. Oh, sorry, it was just starting up. That's why it took long. Okay. There we go. It's also showing you which partitions it's reading from. So remember there are 6 partitions. So it read from the first 3, now it's reading from all 5. So as I said, you have no guarantee between partitions that you'll get sort of perfect balance over messages being read from them. You have guarantees within a partition. But because it's the only consumer, it's now consuming from all 6 partitions, right? And at a rate of about 10, 11,000 messages a second. So I'm going to start up the next one. So now it should, because it's a balanced consumer, what should happen is this one will initially just block for a while because it'll have nothing to consume. Then it'll steal some of the partitions from the other one. So now it's reading the first 3 partitions, and the one I started up initially is reading the last 3 partitions. And you can do that again, and it'll rebalance again. So as I said, very simple, but actually sort of fairly nice behavior for most use cases I've been able to come up with. The throughput drops a little bit, but that's just because I'm running on one machine. Normally would run consumers at least on a different process, on a multi-core system or on a different server entirely. So now each one is consuming 2, and if I kill one of these, then it'll eventually give back its partitions to the other 2. Right, let me just wait for that to happen. There we go. This one got 5 again, and that one got 2 again. Again, you have no guarantees about who's going to get what. That's all sorted out internally. So you don't necessarily know that if you used to have 5, that you will get 5 again, for example. Okay. Right, stop all of that. Time. I'm just stopping it because if I don't, then when I unplug here, I'm going to eventually just drain my laptop battery. Alright, demo. Okay, I'm going to do probably spend another 5 minutes just run through the Python client libraries. I showed you some code, but it's actually almost too simple to show. They're really straightforward to use. So what I'm doing here is there are actually 2 major Python libraries for this, one called PyKafka and one called Kafka Python. That's where you can find them. They're on GitHub, open source, both under the same license, Apache version 2. So I'll do a quick sort of performance comparison between the 2 that I just did on our 3-node cluster in EC2, just to give you some idea. And I'll just go through some pros and cons. And it might not be obvious which one you have to pick. I think it'll depend on what sort of situation you work in. So right off the bat, PyKafka had a version 2 release very recently, Monday. And Kafka Python is at 0.94, and that was released in June. Okay, so PyKafka with the brand new release is more fully featured. So you actually have balanced consumers. So that thing I showed you where partitions get shuffled around automatically, that is a feature of Kafka 0.8.2 and not of 0.8.1. PyKafka is for 0.8.2 only. In fact, it requires 0.8.2 for this reason. Kafka Python can work on older versions of Kafka as well, but it doesn't give you a balanced consumer yet. So they haven't yet taken advantage of the new API for logging offsets in Kafka brokers. So I'm not sure when exactly it's coming. It's definitely in the list, on the issue list. Another advantage of PyKafka is it supports greenlets. So all this async stuff you can either do using features or using threading, or greenlets or using threading. Kafka Python has threading only, so that may or may not be a problem for you. Okay, performance. So, okay, let me just first say what's there and then say why it probably doesn't matter that much. So in PyKafka, for the producer, the median performance is about, on this 3-node cluster in EC2, is about 46,500 messages per second. And then those are the 25th and 75th percentiles, just to give you some idea of range. So it tends to be somewhere between 40 and 50, and it's typically 45. Consumer is a bit slower, so between 12 and 24, so quite a range there for some reason. Median at about 14.5. And I found, so when I downloaded it on Monday, I started playing with it, reported some issues. So I'd say wait for 2.01 until they fixed the bugs in 2.00. But they've been extremely responsive. I was very impressed. So I logged some issues and they were fixed and PR'd and merged 24 hours later. So I just pulled master and been using that. So actually pretty good about that. Okay, Kafka Python producer, so a little bit worse than PyKafka, well, quite a bit worse, so almost 28,000 median rather than 46, and the consumer better, so 37,000 rather than 14. So don't ask me why. I don't understand enough about the internals of either of these two to tell you that. But the reason why it doesn't matter is that actually this is super, super fast, right? This is per second, and it turns out most of your time goes into processing whatever your message is. You probably store it in some sort of format. It might be a protocol buffer. It might be JSON. You have to parse that. Then based on what's in there, you have to decide what you want to do with it. So you probably aggregate it somewhere or you send off another thing. That takes time. And that takes a lot more time than this does. So this is great, but this really isn't the bottleneck. So I wouldn't be too worried about the performance stats, except that it's impressive it can do that much per second. Kafka Python seems to have a less active. I just want to see. So the next slide, one of the pictures. Yeah, there we go. So that's the past 12 months PyKafka and Kafka Python commits to master. So you can see PyKafka sort of started over there. It used to be called something else. It was called Samza over there. I think they changed it because Apache now has a project called Samza with a Z, not a S. So I think that's probably why they changed. So here they started up again. Whereas Kafka Python has sort of been plodding along a bit more regularly, but more slowly. So I'm not sure which of these pictures you prefer. This one is definitely more stable. This one is definitely more active. Depends on what you need. Right, and then last but not least, don't forget Hadoop. There's lots of Kafka support built into the Hadoop stack. So if you use Spark or Spark Streaming or something like that, there are Kafka producers and consumers in there. So you can consume one Kafka topic, do, say, using Spark Streaming, do real-time sort of MapReduce stuff, and they're built in machine learning algorithms or whatever ones you implemented yourself, and then produce it again, results from that to a new topic if you like, or store it somewhere else in HDFS or something. So that's all baked in and is very handy if you live in this sort of space, if you use Hadoop. But you don't have to. So I sort of ignored this for a while because actually this is not a Hadoop talk, it's a Kafka talk. Okay. So I think I'm very nearly out of time, but there are some situations where you don't want to use Kafka. So it's not the tool for absolutely every situation, although some people try and use it in that way. And there's some overhead. So it has all of these cool features about persisting stuff to disk straight away, giving you great, very straightforward replication, taking advantage of the operating system. You might not need all of that. If you have a publish subscribe requirement where you actually really want fire and forget, so you have some sort of distributed stuff happening and you want to log those events, but if one gets lost somewhere, you don't really care. Like it doesn't affect your overall aggregated stats if you use it for monitoring or something like that. You might not want all this overhead. You have to run Zookeeper. You need at least 3 of them because they do leader election, require consensus. You cannot have 2 Zookeeper nodes. If you don't care about resilience, about things falling over and recovering from that, I mean, you should if you're doing anything large, but if you don't, again, you might not care about running a whole cluster dedicated just to handling your publish subscribe stuff. You could use, if I had to recommend something else, which is not Kafka for doing this, it'd be ZeroMQ. If you've never heard about that before, go to zeromq.org and start reading. It is amazing. It is super fast, super lightweight, doing incredible things when it comes to communicating in lots of different patterns. So regardless of whether you're doing client-server, point-to-point, pub-sub, root, it has a ton of different patterns for doing all sorts of awesome stuff for communications. So unless you want some of the other stuff that Kafka offers, you might want to look at ZeroMQ instead. But if you want any of those sorts of things, Kafka is pretty great. Okay, and that is almost it. Right, last one, I promise. So this is just a bit of sort of practical experience from the past 8 months or so, however long we've been using this. So great, now you have this piece of software, it's running, it's awesome, you can interface with it using Python. What are the other things you have to worry about? That's not just the the technical infrastructure. So firstly, I mentioned topics. So you organize events into topics. Each topic has its own partitioned log. You have to think about what your topics are. Why, and this is not a technical problem, this is a design problem. Why would you group certain events together? What is the common denominator? The most useful way I think we've found so far of thinking about it is, ironically, is whether a topic is tends to be either producer-centric or consumer-centric. So the events belong together either because they all come from the same producer. So for example, if the product service is logging state changes in products to something, that's producer-centric because it's about the products, comes from the product service. Other things might want to listen to that for whatever reason, but the topic itself is producer-centric. Or you might have consumer-centric topics. Best example there is user tracking. It's about understanding what users do on your site, regardless of whether they're using the mobile app or the desktop site or whatever. So the events can actually get generated all over the place, but they should end up in the same place because what you use them for, in this case user tracking, is important. So that's sort of a useful way we found about thinking about it so far in terms of organizing our topics. Once you have a topic, you have to worry about what sort of metadata you want to keep track of. So that's things like, do you impose schema or don't you? If you don't, are you happy to live with the potential chaos if somebody pushes invalid messages onto your topic? Do you expect consumers to handle that? Do you expect producers to produce only messages that validate? Kafka doesn't care about any of this stuff. The message is your problem. So it's worth thinking about. Then monitoring. Because things work so well, it's easy to forget to look at them. So what if one of your producers stops producing for some reason? So Kafka won't tell you. It doesn't have a mechanism for telling you. It's just expecting messages to arrive, and they may or may not. So a handy way that we're in the process of implementing for doing that is essentially building an auditing producer and consumer. So we're building a library on top of Kafka, on top of Kafka Python at this stage, although we might transition to PyKafka, that does this other stuff. It imposes schema on the producer side, so you can produce only valid messages. The library will reject them otherwise, so consumers don't have to worry about this. So the auditing idea is basically counting messages. It's a simple counter. So for each producer, count how many messages were produced. Every now and again, so let's say for every 1,000 messages or 10,000, depending on your volumes, produce another message, which is an audit message. It says 1,000 messages got produced. That's all. And it says who? I'm a producer. I have a name. I say I produce 1,000 messages, and then the auditing consumer listens to absolutely everything, and it checks whether it sees enough messages for that to make sense. So it's not actually trying to check whether every single message arrives, but it will tell you if you're starting to lag. So if producers are producing messages, but your auditing consumer isn't picking them up, there's something wrong somewhere. It doesn't tell you exactly where, but it gives you some idea. If you don't do that sort of thing, and we've run into this once or twice already, it's very easy to sort of 24 hours after the fact realize, oh, wow, we haven't, why are these values so low? Oh, it turns out one of our producers or one of our consumers fell over, and it's one of 3, so we're only actually seeing 2/3 of the data on our aggregated dashboard. So that's a real example. That's actually happened. But you don't really know unless you track, somehow try to track how much is being produced and how much is being consumed. So this is still a work in progress, but just a bit of practical experience. And then the last one is, especially in a larger team, you probably want to hide most of this sort of complexity from the rest of the team. They should be involved in the design process, but when they're writing code, they shouldn't have to write more lines of code just because you're imposing more structure. The structure goes into the metadata. You should have something that manages that, but your developers shouldn't have to worry about that. And then just sort of having experiences from the other end. Part of the reason for that is devs are time-pressured, cranky, stubborn people. If something doesn't work now, and if it's not straightforward to start using it, there's a good chance they won't, maybe until next week once their deadline is passed. And then you just built up technical debt. So if you don't make things as simple and straightforward as possible for your dev team, you build up technical debt within a team. And on that note, I will finish. And there are a couple minutes left for questions, I think. Thanks.
Great.
Range there for some reason. Median at about 14.5. And I found, when I downloaded it on Monday, I started playing with it. reported some issues. So I'd say wait for 2.01 until they fix the bugs in 2.00. But they've been extremely responsive. I was very impressed. So